The
S7 1200 is the basic controller from Siemens for many small to medium-sized applications in an industrial environment as well as in other fields. It's particularly notable for a wide array of integrated functionalities. First of all, it includes numerous communication functions. It supports Profinet I/O communication as well as Modbus TCP communication. Other features include the integrated function of PID controls or pulse outputs or even high-speed counters. Today, we would like to introduce an application that illustrates the high-speed counters functionalities in a more striking fashion. To accomplish this, Peter has set up an experiment, and he'll now explain to us what he's devised and where something like this might be used.
Before we begin, I would like to say a few words about how the high-speed counters work in the first place. First, we have various types of inputs on the S7 1200. We have the inputs on board on a CPU 1217. CPU 1217 is a controller for faster applications, i.e., for faster motion applications. The inputs go up to 100 MHz because they are a differential signal located on the voltage hub. Then we also have inputs on the signal board of the S7 1200 for 5 volts. They go up to 200 kHz. And then we also have the normal inputs on the S7 1200, which go up to 100 kHz. In our case, we're going to use the normal inputs, so we can initially demonstrate basic capabilities. When an input comes, the counter increases by 1 for each pulse of this input. If a second input comes, the counter decreases by 1. This means you can configure it in different ways. In addition, if we take a look here, we also have a gate input, so everything can be configured via the hardware config of the CPU, via the gate input, you might say. When the pulses arrive, they come continuously if the gate input is active. Only those pulses are counted. You can see this here in our display. When the pulses come, i.e. from the moment at which the sensor recognizes the workpiece, it begins to count, and the counter stops counting as soon as the workpiece has passed by, even though the pulses arrive continuously. The normal application is such that you essentially have a counter, or this workpiece on a conveyor belt. Here you can see what this would look like. Here we have a rotary encoder, and connected to the rotary encoder is a high-speed counter that feeds into these inputs of the CPU. A workpiece would be lying there, and a motor would move it. And the workpiece would essentially move along this conveyor belt. And the rotary encoder would recognize how far the workpiece has traveled. Here we can see the display, so let's set the workpiece into motion. Here we have this high-speed counter on this rotary encoder, and now the workpiece is approaching. As soon as the workpiece is positioned in front of this gate input, you can see that it is starting to count in the current count at the top. Once the workpiece has passed by, it stops counting, and then we know the precise length of the workpiece, because we know that each pulse has a particular length. This enables us to precisely determine the length of the workpiece. Once it has passed by, we will now also see that the value for current count has been stored. This whole thing was too complicated for me in my application here, because I did not want a motor. I simply wanted to solve the problem differently, while also including the counter. So what I actually wanted to measure is essentially a workpiece, such as this pen here. I have 2 light barriers, and when I drop this pen, I want to determine as it is falling how long the workpiece is, in this case the pen. So I take the first input, that's the capture input. I generate pulses from the output of the CPU, the output is here, and feed the pulses directly to the input, which means I can already do without the rotary encoder. I essentially have a time base, which means each pulse has a specific time, and when the workpiece passes by, I can essentially measure the time that elapses starting from the moment that it passes in front of the gate input, as a workpiece falls by, and until it has completely passed. I count the pulses during the entire interval. Because I know the length of the pulses, I know how long the pen was in front of the initial input, in front of the gate input.
But how do I illustrate this model on your test setup?
Well, I use a second input because while I do know how long the pen is in front of the input, I still have no measurement of the speed and no length at all. I need a second light barrier. That's to capture input signal. We'll drop the pen again. When it reaches the first light barrier, it will begin counting, and when it reaches the capture light barrier, the counted value will be copied into the current count value of the capture input. The fact that we know the distance between the two light barriers means we can basically determine the speed of the pen at the moment that it falls past the sensor. So we count the pulses. When it starts counting, it is here, we copy these pulses, and this tells us the speed of the pen at that point. And once it has passed, we essentially know how many pulses were counted and how much time elapsed while it was in front of this light barrier.
That sounds really easy. I don't need to spend any additional time on configuration since it's all integrated in the counter functionality.
Right. It only involves configuration.
And you've now tried to illustrate all this in a model. If I understand this correctly, then you've now mounted the light barriers here that reflect the corresponding counter inputs here and illustrate a real-life scenario.
Yes. The first light barrier is a gate light barrier. The second is a capture light barrier. And the third is a sync light barrier, which I actually only need in order to reset the whole thing. So the pen will now arrive, pass through the first light barrier. Then the model measures the pulses between the first and the second barrier. The number of pulses can then be used to determine the speed. Once it has left the entire area, I have the length of the pen, and once it is completely through, the whole thing is reset, allowing me to perform the routine again. Now we're going to test the whole thing. We're dropping a pen through it. That was too fast for you. And now if we take a look, we can see here that the counted pulses are roughly 25,000. And here we have the speed at 1.9 meters per second, and the length of the pen is 0.162 meters.
So that means 16 centimeters. So if I now measure it again using my ruler, I discover that it's almost exactly 17 centimeters instead of the 16 indicated here. Is there a minor uncertainty factor in the measurement configuration? I think that due to the slanted plane, we can't reach a constant speed because of the Earth's gravity.
Yes, that's the problem. After all, we are measuring the speed from the tip of the pen. Yet afterwards it keeps on accelerating, which is why the overall measurement result is not accurate. The idea was basically to slow down the pen by putting a constant brake on it. All I could think of was an eddy current brake, or in this case, a magnet. Even though aluminium is not magnetic, if the magnet is in motion in the aluminium, it practically creates its own current in the aluminium, which in turn generates a magnetic field, slowing the pen down and bringing it to a more or less constant speed. If we drop it, it travels through a fairly constant speed. Now if we measure this pen and compare it with the value here, then we hopefully come up with
almost exactly 17 centimeters. Yes, 16.9.
Now if we look at the whole thing, I have noticed here also with the slow pen, we get 8,600 pulses for the distance between gate and capture. And I noticed that we ought to do it more quickly.
Oh.
So we need something to accelerate the pen. And I arrived at another solution. How can you make the pen faster? So one option is to make the whole thing longer and not brake. But there are also other possibilities. Here we have acceleration. I thought about it. You could suspend something there at the top. We all remember that from when we were kids. We suspend the rubber band here.
Now we're going to burn rubber.
So now we are taking another pen that has a notch in it. Let's try to get it through there.
That was damned fast.
Yeah.
Can we see that anywhere here?
Yes. We can see 7.5 meters per second, length 26.77.
Okay, so together, let's check to see what the ruler has to say. I'm measuring almost exactly 27 centimeters.
Yes. We also see it there. And we can see that for the 50 millimeters, we still have 672 pulses. That means it will also work much more quickly.
Thanks, Peter. In summary, with the SIMATIC S7 1200, Siemens offers the optimal solution for small to medium-sized tasks. The integrated functions of the SIMATIC S7 1200 offer an outstanding basis for this.
Siemens. Ingenuity for life.